about quark-gluon plasma?
That's bad. That's bad for physics. For the cosmic microwave background, the leftover radiation from the Big Bang.
But you would like something more that you could bring to people, saying that this is very valuable and tangible stuff.
And we had very good reason to hope that we could detect it by now in an underground lab.
In the shadow of the Swiss Alps lies the European Organization for Nuclear Research, commonly known as CERN. Here, nestled deep underground, the Large Hadron Collider stretches its circular arms across nations, a titan of human curiosity and ingenuity. It is the modern cathedral of science, where the high priests of physics gather to unravel the tapestry of the cosmos. And recently, in a world-shattering revelation, podcast kingpin Joe Rogan just unveiled that something unexpected happened at CERN, raising questions even the experts struggle to answer. But what exactly did they find? What could this discovery mean for our understanding of the universe? Join us as we dig deep into something terrifying that has been found at CERN that scientists cannot explain. According to the Big Bang, the theory reigns supreme. As the sole surviving explanation for the history of the cosmos, our universe began as a singularity, an infinitely dense and hot point, approximately 13.8 billion years ago. At this initial moment, something like 1/100th of a billionth of a trillionth of a trillionth of a second, it underwent an incredible growth spurt. During this burst of expansion, which is known as inflation, measurements of the expansion during this time are extremely hard to comprehend. It seems that the universe grew by some 100 million billion times. That's a 1 followed by 26 zeros. Things at this point are really strange. Energy exists, but light as we know it does not. That's because light is a wave that travels through space, and there is no open space yet. In fact, space is so crammed full of high-energy phenomena right now that matter itself cannot yet exist. Sometimes astronomers refer to the universe during this time as soup, because it's just so hard to imagine how thick and energetic it would have been. But even soup is a poor descriptor. The cosmos at this time is thick with energy, not matter. The most important thing to understand about the inflation era is that anything that was just a little bit different before inflation will become something that is a lot different later. After inflation, the universe continued to grow, but at a slower rate. As space expanded, the universe cooled and matter formed. Light chemical elements were created within the first 3 minutes of the universe's formation. As the universe expanded, temperatures cooled, and protons and neutrons collided to make deuterium, which is an isotope of hydrogen. Much of this deuterium combined to make helium. For the first 380,000 years after the Big Bang, however, the intense heat from the universe's creation made it essentially too hot for light to shine. Atoms crashed together with enough force to break up into a dense, opaque plasma of protons, neutrons, and electrons that scattered light like fog. About 380,000 years after the Big Bang, matter cooled enough for electrons to combine with nuclei to form neutral atoms. This phase is known as recombination, and the absorption of free electrons caused the universe to become transparent. The light that was unleashed at this time is detectable today in the form of radiation from the cosmic microwave background. Yet, the era of recombination was followed by a period of darkness before stars and other bright objects were formed. Roughly 400 million years after the Big Bang, the universe began to come out of its dark ages. This period in the universe's evolution is called the Age of Reionization. This dynamic phase was thought to have lasted more than 500 million years, but based on new observations, scientists think reionization may have occurred more rapidly than previously thought. During this time, clumps of gas collapsed enough to form the very first stars and galaxies. The emitted ultraviolet light from these energetic events cleared out and destroyed most of the surrounding neutral hydrogen gas. The process of reionization, plus the clearing of foggy hydrogen gas, caused the universe to become transparent to ultraviolet light for the first time. Although the expansion of the universe gradually slowed down as the matter in the universe pulled on itself via gravity, about 5 or 6 billion years after the Big Bang, a mysterious force now called dark energy began speeding up the expansion of the universe again, a phenomenon that continues today. And a little after 9 billion years after the Big Bang, our solar system was born. Amazingly, this fantastical story holds up to all current observations. Astronomers have done everything from observing the leftover electromagnetic radiation from the young universe to measuring the abundance of the lightest elements and found that they all line up with what the Big Bang predicts. As far as we can tell, this is an accurate portrait of our early universe. But as good as it is, we know that the Big Bang picture is not complete. There's a puzzle piece missing, and that piece is the earliest moments of the universe itself. That's a pretty big piece, and that's why CERN's Large Hadron Collider was born. The Large Hadron Collider, or LHC, often hailed as the most complex machine ever built by humankind, is a marvel that transcends mere scientific pursuit. It is the heart of CERN, pulsating with protons that dance at velocities unfathomable in a choreography dictated by the laws of quantum mechanics. The collider's primary quest is to validate the standard model of particle physics and to probe the elusive mysteries that linger beyond its scope. It can reproduce the conditions that existed within a billionth of a second of the Big Bang. The colossal accelerator allows scientists to collide high-energy subatomic particles in a controlled environment and observe the interactions. One of the most significant LHC breakthroughs came in 2012 with the discovery of the Higgs boson, which is also known as the God particle. The long-sought-after Higgs is the missing link in the reigning theory of particle physics, known as the Standard Model. The Higgs boson was first proposed in 1964 as an explanation for why subatomic particles like electrons have mass. The media hubbub surrounding the Higgs boson died down fairly quickly. However, in the physics community, things were just heating up. While physicists felt certain that they had found the Higgs boson, they weren't 100% sure. The data was preliminary, and to be completely certain of their success, cross-checks needed to be made. Over the following decade, many measurements supported their initial claim. But a new measurement made by scientists analyzing data recorded at the CERN laboratory in Europe could be telling a new story. Accepted theory predicts that the Higgs boson can decay in several different ways, with each decay occurring at a different rate. Many of the predicted decays have been observed and their rates measured, and the data agreed well with predictions. Theory predicts that for every 10,000 decays of the Higgs boson, 15 decays should be into a Z boson and a photon. Because Higgs bosons are themselves rare, finding this particular decay is very difficult. To improve the odds of seeing this rare decay, scientists combined data from two gigantic detectors, ATLAS and CMS. Together, we found evidence that we had observed the decay of Higgs bosons into Z bosons and photons. But much to our surprise, we found that the decay rate was much higher than expected. Their measurements said that this decay occurred about 34 times out of every 10,000 Higgs boson decays. This is 2.2 times the theoretical value. So what could this mean? It could just be a statistical fluke. That kind of thing happens in real physics measurements, but it could also mean that researchers are seeing the first hints of unknown physics. Higgs bosons do not directly decay into a Z boson and a photon. The actual decay is a multi-step process. For example, one way this can occur is that the Higgs boson decays into a pair of very heavy particles called top quarks. After that happens, one of the top quarks emits a Z boson, and the quark merges with the other one, and they turn into a photon. The process is essentially a little loop of top quarks that separates the Higgs boson and the two decay products. This top quark loop is not the only way in which the decay can occur. Other particles can also form part of the loop. And this is one possible explanation for the observed excess of this kind of Higgs boson decay. It might be that there are unknown particles, ones that haven't been discovered yet, that also can form a decay loop. So, the observation of an excess of events in which Z bosons and photons are made could be the first hint of brand new physics. Not only that, finding the Higgs has another significant implications. It opens the door beyond the Standard Model for explaining the existence of dark matter, the mysterious substance widely thought to make up 27% of all matter in the universe. What's notable, dark matter is completely invisible. It emits no light or energy and thus cannot be detected by conventional sensors and detectors. The key to its elusive nature must lie in its composition, scientists think. Visible matter, also called baryonic matter, consists of baryons, an overarching name for subatomic particles such as protons, neutrons, and electrons. Scientists only speculate what dark matter is made of. It could be composed of baryons, but it could also be non-baryonic. That means consisting of different types of particles. Most scientists think that dark matter is composed of non-baryonic matter. The lead candidate, weakly interacting massive particles, termed WIMPs, are believed to have 10 to 100 times the mass of a proton, but their weak interactions with normal matter make them difficult to detect. Neutralinos, massive hypothetical particles heavier and slower than neutrinos, are the foremost candidate, though they have yet to be spotted. Sterile neutrinos are another candidate. Neutrinos are particles that don't make up regular matter. A river of neutrinos streams from the sun, but because they rarely interact with normal matter, they pass through Earth and its inhabitants. There are 3 known types of neutrinos. A fourth, the sterile neutrino, is proposed as a dark matter candidate. The sterile neutrino would only interact with regular matter through gravity. The smaller neutral axion and the uncharged photinos, both theoretical particles, are also potential placeholders for dark matter. There is also such a thing as antimatter, which is not the same as dark matter. Antimatter consists of particles that are essentially the same as visible matter particles, but with opposite electrical charges. These particles are called antiprotons and positrons, or anti-electrons. When antiparticles meet particles, an explosion ensues that leads to the 2 types of matter canceling each other out. Because we live in a universe made of matter, it is obvious that there is not that much antimatter around. Otherwise, there would be nothing left. Unlike dark matter, physicists can actually manufacture antimatter in their laboratories. But if we cannot see dark matter, how do we know it exists? The answer is gravity, the force exerted by objects made of matter that is proportional to their mass. Since the 1920s, astronomers have hypothesized that the universe must contain more matter than we can see, because the gravitational forces that seem to be at play in the universe simply appear stronger than the visible matter alone would account for. As Peter Van Dockum, a researcher at Yale University, said in a statement, "Motions of the stars tell you how much matter there is. They don't care what form the matter is, they just tell you that it's there." Astronomers examining spiral galaxies in the 1970s expected to see material in the center moving faster than at the outer edges. Instead, they found the stars in both locations traveled at the same velocity, indicating the galaxies contained more mass than could be seen. Studies of gas within elliptical galaxies also indicated a need for more mass than found in visible objects. Clusters of galaxies would fly apart if the only mass they contained was the mass visible to conventional astronomical measurements. Different galaxies seem to contain different amounts of dark matter. In 2016, a team led by Van Dockum found a galaxy called Dragonfly 44, which seems to be composed almost entirely of dark matter. On the other hand, since 2018, astronomers have found several galaxies that seem to lack dark matter altogether. The force of gravity doesn't only affect the orbits of stars and galaxies, but also the trajectory of light. Famous physicist Albert Einstein showed in the early 20th century that massive objects in the universe bend and distort light due to the force of their gravity. The phenomenon is called gravitational lensing. By studying how light is distorted by galaxy clusters, astronomers have been able to create a map of dark matter in the universe. A vast majority of the astronomical community today accepts that dark matter exists. But how do they look for dark matter? Well, since we don't know what dark matter is, the answer is, for every possible candidate for the dark matter, there is a different strategy to search for it. People build giant detectors deep underground to get away from all the other particles streaming through the environment around us, and look for signals of the dark matter hitting their detector after passing through the Earth overhead. That's also why CERN's Large Hadron Collider is the ideal place to search for it. With the switching back on of this machine after a 3-year hiatus, the Giant Particle Accelerator has a new target set in its sights: the hunt for dark matter, the mysterious substance that must make up about 80% of all the matter in the universe, but which no one has ever seen. As Gian Guidice, who leads the theoretical division at CERN, told a press conference, since the discovery of the Higgs boson, the field of dark matter has changed completely. Now, physicists are considering all manner of explanations for dark matter, including exotica such as a quasi-form of radiation called dark radiation, with wavelengths extending to several light years to mini black holes, modified gravity, supersymmetric particles, and other kinds of exotic matter. Despite these new theories, it seems reasonable to still consider some type of particle as being a leading contender for the identity of dark matter. In the words of Victoria Martin, a professor of particle physics at the University of Edinburgh, Scotland, we think there has to be other particles that we haven't discovered yet, which aren't part of the standard model, but which could make up dark matter. The Higgs boson, discovered by the LHC 10 years ago, could be the key. The Higgs boson is the mediator of the Higgs field, which is a universe-spanning field of energy from which massive particles draw their mass by interacting with the Higgs boson. As we know, dark matter is extremely shy and retiring, only interacting with the rest of the universe through gravity. We can't see it otherwise, which makes detecting it a problem. If it is a WIMP, however, then it must surely get its mass from the same source as other massive particles, specifically the Higgs field. This propels the Higgs boson to the forefront of dark matter research, a probe into the dark realm that was impossible just 12 years ago, when the LHC was first switched on. The idea is that if dark matter is interacting with the Higgs field, then we might see through one of the LHC's experiments the Higgs boson decaying into dark matter. However, whereas once WIMPs were everybody's favorite explanation for dark matter, the possibility of lighter particles, such as hypothetical particles called axions, are now back on the drawing board. As Jamie Boyd, spokesperson for the LHC's FACER or Forward Search Experiment instrument, said, "There's a huge range of masses that dark matter could have. Suppose that the dark matter particle was a lighter particle, such as an axion. It would require lots of these particles to fill the universe with all the dark matter that gravity suggests is there, and therefore the characteristics of a light dark matter particle would have to be very precise, with particular values for their mass and their coupling." FACER is looking at the light end of this, where the mass and coupling are small. But what FACER looks for isn't so much the dark matter particle itself, but what we call its mediator. Just as the Higgs boson mediates interactions between particles and the Higgs field, and photons allow the electromagnetic field to couple to particles, the dark matter mediator would allow dark matter to talk to other particles in the standard model. Different types of mediators have been theorized, distinguished in part by their quantum spin, but the mediator that FACER is specifically tailored to detect is the hypothetical and mysterious-sounding dark photon. According to Boyd, the dark photon could be produced in the collisions in the LHC. As its name suggests, the dark photon would be extraordinarily difficult to detect directly. Instead, the idea is that after a dark photon has been produced in a collision between heavy ions in the LHC, the dark photon would subsequently enter the phaser instrument, where there is a chance it could interact with a dense tungsten target and decay into a bunch of ordinary standard model particles that FASER can more easily detect. Essentially, a bunch of standard model particles would appear to burst into existence out of thin air. They could be the smoking gun that a dark photon has slipped through undetected. It's a long shot, but even a null result would provide valuable information to scientists. Theoretical predictions for the mass energy of dark photons are quite wide. The LHC would be able to at least rule out large swathes of those possibilities, further constraining where the dark photon and dark matter particles might be hiding. Elsewhere, a team of experts led by physicist Deepak Kar and postdoctoral researcher Sukanya Sinha have pioneered a whole new way of searching for dark matter by CERN's LHE. According to their team's new study, we may be able to find evidence of dark matter mixed into standard model particles, the ones that make up everything we can see and touch. Now, this isn't going to be some kind of bang-zoom easy fix. It's still dark matter after all. Nothing is straightforward. It's a wild shift away from the ways we usually hunt for evidence of dark matter. But maybe a wild shift is what we need. It's not like we've had much success with the standard methods. There have been plethora of collider searches for dark matter over the past few decades that so far have focused on WIMPs. Enter the idea of the semi-visible jet. When protons collide inside of a particle accelerator, they basically break up into other, even smaller particles like quarks and gluons, and then decay into jets of fundamental particles. In theory, those collisions could also produce the dark matter versions of quarks and gluons, which would then decay into semi-visible jets. Jets where some of the energy is made of standard model particles, and some of the energy is made of dark particles. Jets are produced in matching pairs, so if you produced a pair of jets in a collision and one of the jets was weaker than the other, the missing energy would be dark matter, as long as it wasn't a technical flaw in the readings. We could measure dark matter by measuring the energy we didn't detect. Convoluted? Maybe, but radical ideas often are. This method would be probing into an entirely different regime of dark matter particles than almost every other collider-based dark matter experiment. Most of these experiments look for what are called WIMPs, or weakly interacting massive particles of dark matter. But the semi-visible jet route of study looks for strongly interacting dark matter particles like dark quarks and dark gluons. So far, the team hasn't found any semi-visible jets, nor the particles that form them. But no one has found any WIMPs either, and experts have spent a whole lot more time looking for those. Studying dark matter is still incredibly theoretical, but this particular avenue of study is exciting enough that CERN's Atlas collaboration has designated this new paper one of its flagship results, and there will almost certainly be more experiments looking for semi-visible jets. As Sinha said in the press release, even though my PhD thesis does not contain a discovery of dark matter, it sets the first and rather stringent upper bounds on this production mode and already inspiring further studies. Now we just wait to see what those studies turn up. Meanwhile, it is worth noting that planning is well underway for the successor to the world's most powerful particle accelerator. The new atom smasher, named the Future Circular Collider, or FCC for short, will dwarf the LHC in size and power. It will smash particles together with so much energy, in fact, that scientists say it may be capable of investigating our universe's most mysterious entities, dark energy and dark matter. LHC operators at CERN revealed the results of a midterm review of their FCC feasibility study to the press on February 5th. The feasibility study began in 2021 and is set to conclude in 2025. The findings thus far constitute 3 years of work, with scientists and engineers from across the globe determining the placement of the new accelerator's ring, the implementation of the FCC facility, concepts for detectors and funding aspects. The FCC will run under the jurisdiction of France and Switzerland, just like the LHC currently does, but the future accelerator will stretch 90.7 kilometers, making it over 3 times the length of CERN's current particle accelerator, which is 27 kilometers long. The LHC is the largest and most powerful particle accelerator in the world. The FCC will operate in the same way as the LHC, accelerating charged particles around a loop using superconducting magnets, then smashing them together as they approach the speed of light. Scientists can probe fundamental physics by observing showers of secondary particles created when particles like protons slam together. But whereas the LHC can attain energies of around 13 tera-electron volts when operating at full power, CERN says the FCC should be able to reach energies as great as 100 tera-electron volts. As CERN Director General Fabiola Gianotti said at February interim report presentation in Geneva, "Our aim is to study the properties of matter at the smallest scale and highest energy." But why do particle accelerators need more power? Well, as told, the crowning achievement of the LHC thus far is undoubtedly the discovery of the Higgs boson, the force-carrying particle of a field called the Higgs field, which permeates the universe and dictates most other particles' masses. The breakthrough sighting of the Higgs boson by 2 LHC detectors was announced on July 4, 2012, and is credited with completing the standard model of particle physics, which is humanity's best description of the universe, its particles, and their interactions on a subatomic scale. However, the standard model still requires some tweaking, and since 2012, scientists have been using the LHC to search for physics beyond the model to make those adjustments. Success has been limited. This search will get a boost when the LHC's high luminosity upgrade is completed, which will mean the particle accelerator can perform more collisions and offer scientists more opportunities to spot exotic physics. The 2 main outliers of the standard model, aka why some of those tweaks are necessary, are dark matter and dark energy. Sometimes collectively known as the dark universe, these phenomena constitute such large mysteries for scientists because dark energy accounts for around 68% of the universe's energy and matter, while dark matter accounts for around 27% of these continents. But neither can be seen because they don't interact with light, and no one has been able to pin them down through other forms of direct detection either. That means that the matter and energy we understand and can account for comprise no more than 5% of the universe's contents, and we have little idea what around 95% of the universe actually is. And probing these aspects of the universe may require smashing particles together with much more energy than the high luminosity LHC is capable of. To begin with, dark matter can't be standard matter, like the atoms that make up the stuff we see around us on an everyday basis, like stars, planets, and our bodies. Remember how it doesn't interact with light? Well, protons, neutrons, and electrons, collectively known as baryons, do. So dark matter must be something else. Currently, the only way scientists can infer the presence of dark matter is via its interaction with gravity and the effect this has on baryonic matter, and, in turn, light. Dark energy is even more problematic. It's the force that scientists see driving the acceleration of the universe's expansion. It concerns a period of expansion separate from the universe's initial inflation, which was triggered by the Big Bang. After that early expansion slowed to a near halt, in a later epoch, the universe unexplainably started to expand again. This expansion rate is actually speeding up to this day, with dark energy used to account for that action. However, as we've discussed, scientists don't actually know what dark energy is. To see why that is troubling, imagine pushing a child on a swing. The Big Bang is akin to your first and only push that gets the swing in motion. The swing may keep going for a short while, even without any action from you. Then it will come to a half. Then, imagine that it suddenly begins motion again, despite you just standing there. And not only that, but it swings faster and faster, reaching higher and higher points. This is similar to what dark energy is doing to the very fabric of space. CERN hopes the high-energy collisions of the FCC could reveal the nature of this ongoing late-universe push and the particles that make up dark matter. But it will be some time before this future particle accelerator is ready to embark on its investigation of the dark universe. According to the timeline in 2028, 3 years after the completion of the FCC feasibility study, CERN member states will convene to decide if the FCC will get the go-ahead. Should the future collider get greenlit, CERN says, construction will begin in the mid-2030s. The FCC will be completed in stages. The first stage is an electron-positron collider, or known as FCCEE, that will slam together negatively charged electrons, their positive antiparticle counterparts, known as positrons and other light particles. CERN adds that FCCEE should start operations in 2045. The second machine of the FCC will be a proton colliding accelerator sitting alongside the FCCE in the same evacuated tunnel buried under the French-Swiss Alps and Lake Geneva. According to CERN, this part would come online no sooner than 2070. At the CERN press conference, Gianotti laid out some of the costs of the FCC, saying that the first FCCE stage alone would cost an estimated $17 billion USD. CERN's Director General justified the cost by adding that the FCC is the only machine that would allow humanity to make the big jump in studying matter needed to crack the secrets of the dark universe. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content